In this video we will look at floating point binary numbers. Now in our previous video we looked at fixed point binary to represent fractional numbers, but this method came with a bit of a drawback. We had to compromise between the range of numbers that could be represented and the accuracy of those numbers. But there is another method of representing fractional numbers in a far more flexible and efficient way, and that's known as floating point binary. Now, before we move into floating point binary, let's just remind ourselves of standard index form, which you may have done lower down in the school. So when numbers get really big, it can be quite annoying to write down strings of zeros and zeros and zeros. And what mathematicians and scientists sometimes prefer to do is to write long numbers in a kind of shorthand known as standard index form. So if you imagine this value here, we could actually rewrite that as 0.3943 times 10 to the 12. Now remember, times 10 to the 12 means effectively move the decimal place to the right 12 places. So if you started off with 0.3943 and then you move that decimal point 12 places to the right hand side, you would end up with that original number. So standard index form is a really neat and tidy way of representing large numbers. Now, mathematical statements in standard form can be split into two parts. We've got the mantissa and we've got the exponent part. Now, the mantissa is the result of where the original number's being converted to a form where its most significant figure is after the decimal point. And the exponent is the order of magnitude, and it says effectively how many places to the right the decimal point needs to be moved in order to recreate the original number. Now, this same principle underpins floating point binary representation. So if we had 16 bits that was used to represent a floating point binary number, it might be that we have 8 of those bits to form the mantissa and 6 to be the exponent. Here's an example of that. You can see here that we've got the mantissa where the decimal point is after the first 0, and then we've got the fractional parts to represent the mantissa. And then on the right hand side, those 6 bits are representing the exponent, the order of magnitude. Now, as floating point binary numbers are usually represented in 2's complement, so that it can both represent positive and negative numbers, the leftmost bit of both the mantissa and the exponent is a sign bit, and you can see here that the place values, the column value, is -1 for the mantissa on the left hand side, -32 in this case for the exponent, because there are 6 bits for the exponent. So let's have a look to see how we can read a floating point binary number and convert it into denary. So if this is our floating point binary number, the way that I go about trying to read this and see what it actually represents is I would rewrite the number in standard form. So 0.11010000 times 2 to the 11, or 2 to the 3 in binary. Now, before we saw it was times 10 to something. That's because we were dealing with denary, that's base 10. We're dealing with binary here, so it's times 2. And obviously that binary value 11 is actually 3, so it's times 2 to the 3. Now 2 to the 3, that's the order of magnitude. That just means move the decimal point to the right 3 places. So if we get our mantissa and we move the decimal point to the right 3 places, we end up with 110.1. We can ignore the zeros that follow that. So 110.1 is the value that this floating point binary number is representing, and that's 6.5 because it's one lot of 4, one lot of 2, no ones, and then one lot of a half, so 6.5. Let's have a look at another example. Again, same method. rewrite the number in standard form. So that's times 2 to the 4. We then get our mantissa and we move the decimal place 4 places to the right, leaving 1011.1. And then we just convert that binary into denary if we want to read it ourselves, and that is 11.5. So here's another example, but this time you can see that the mantissa is negative. That sign bit is a 1. So what we do first of all is we know that the mantissa is in 2's complement. We'll convert that back into its sort of positive form, if you like. It's still negative, but we can start to actually recognize the value, the binary values, more easily. So we would subtract 1, and then we would flip the bits, because to go from 2's complement back, we do the opposite. So subtract 1, flip the bits, and we end up with 0.1001. So rewrite it in standard form. We have minus 0.1001 times 2 to the 3. That means move the decimal point 3 places to the right. So minus 0.1001 would become minus 100.1. And if we were to convert that into denary, that would end up being minus 4.5, because it's one lot of 4 and one lot of a half, but obviously it's negative, so it's minus 4.5. Let's have a look at another example, but this time a negative exponent. So we've got our mantissa, we've got our exponent, it is in 2's complement. You can see that it is negative because the leftmost bit is 1. So we convert 2's complement of that negative number into its positive form, so we know what we're dealing with. So 111101. If we were to subtract 1, would become 111100. And then if we flip the bits, we end up with 000011, which is 3. Well, it's still negative, so it's minus 3. So we rewrite the number in standard form. So that's 0.1011, that's the mantissa, times 2 to the minus 3. Now, when we're dealing with negative exponents, it's telling us to move the decimal point, but negative means move it to the left if we want to get back to the original number. So we move that decimal point to the left 3 places. So 0.1011 would become 0.000111. And we can now just convert that into binary, and it means that we've got nothing under the half, nothing under a quarter, nothing under an eighth. We have 1 under a 16th, we have 1 under a 64th, 1 under a 128th, and if you add those together, you end up with 0.0859375. Okay, let's have a look at normalisation. So whenever we deal with floating point numbers, we want to be able to use the available bits as efficiently as possible, so that we can always store a number as precisely as possible with a given number of bits. Now, normalisation is a process of ensuring that floating point numbers are stored as precisely as they can be, as efficiently as they can be, and it's done by placing the first significant figure of the mantissa after the decimal point. So if you think about these values here, 223.345 times 10 to the 3, and you've got this value here, 2.23345 times 10 to the 5, and 0.02233345 times 10 to the 7. If you were to actually move the decimal points according to the exponents, you would end up with exactly the same value. But none of them are in a normalized form. If it's in a normalized form, the most significant bit has to be after the decimal point. So to write this value or these values as a normalized, or in a normalized form, I should say, it would be 0.223345 times 10 to the 6. And it's exactly the same idea when we're dealing with floating point binary numbers. So in binary, remember, if it's in a positive number, the mantissa sign bit is 0, and the next digit is 1. So if the sign bit's 0, we then have a decimal point, and the next would have to be 1 if it was going to be normalized. So that would be normalized because the most significant bit, this first 1, is after the decimal point. Now in a negative number, remember that the mantissa sign bit is 1. So the most significant bit would be the first 0 after that sign bit. Like so. Now remember, if you move the decimal point to the right in the mantissa, you must reduce the exponent accordingly. Remember, the exponent tells us how many places to the right we need to move the decimal point to get to the original number. So if we move that decimal point to the right already in the original number, then, or in the mantissa I should say, then we need to reduce the exponent accordingly. And again, if we move the decimal point to the left in the mantissa, we must increase the exponent accordingly. So let's have a look at a couple of examples. Let's normalize the following floating point number. So here you can see that the mantissa is positive. The exponent is 5 times 2 to the 5. Now if we want to make the mantissa, put this floating point value into a normalized form, we need the decimal point to be after or before the most significant bit, after this 0 here. So it needs to move 2 places to the right. Now if you move the decimal point 2 places to the right, you have to reduce the exponent by 2. So to normalize the mantissa, the decimal needs to be moved 2 places to the right, like so. And we therefore need to reduce the exponent by 2. So the result would be this floating point binary value. And if we look at another example of normalization, but in a negative number, negative mantissa, you can see here that the leftmost sign bit is 1, so it's definitely negative. The most significant bit, therefore, in the mantissa is this 0 here. So we need to move the decimal point, so it is just before that most significant bit. So we move it 1, 2, 3, 4 places to the right hand side. Therefore we need to reduce the exponent by 4. So to normalize the mantissa, we move it 4 places to the right like we've done here. We now reduce the exponent by 4, so it goes from 5 down to 1. The result therefore is the following floating point binary number. And that's an example of normalization for both positive and negative mantissas.